A galaxy 13 billion light-years away is sending photons into your eyes at this very moment. The hydrogen in your blood was forged in the first 3 minutes after the Big Bang. Every electron in your body vibrates in a field that stretches to the edge of the cosmos. Today we trace the invisible threads connecting you to quasars, to colliding black holes, to particles you will never see. If you enjoy physics that actually makes sense, subscribe and stay close. The universe is not a place you live in. You are woven into it. Let's begin. Hold up your hand. Look at it. Every atom in those fingers was once packed into a space smaller than a grain of sand, pressed against every atom that would later become the sun, the moon, and a galaxy you will never visit. This is not a poetic image. It is a direct consequence of what the Big Bang actually was. We often picture the Big Bang as an explosion in space, a giant firework going off in some dark room. That picture is wrong, and fixing it is the first step toward understanding how you are connected to galaxies billions of light-years away. The Big Bang was not an explosion in space. It was an expansion of space itself. Everything that exists today, every star, every planet, every atom in your eyelashes was contained in a single, incredibly hot, incredibly dense state. There was no outside. There was no empty room around it. Space itself was that tiny blazing point, and then space began to stretch. Think of it this way. Imagine a sheet of rubber with dots drawn on it. Now stretch the rubber in every direction. The dots move apart, but none of them is at the center of the stretching. Every dot sees every other dot moving away. That is how the universe expands, and if you run that expansion backward, every dot converges. Every dot was, at one moment, pressed against every other dot. You're made of dots. The atoms in your left hand, the atoms in a distant quasar, the atoms in the dust between galaxies, all of them shared the same tiny volume at the beginning. They were in direct contact. They exchanged heat. They exchanged particles. They were, in the most literal physical sense, the same system. Now, the atoms themselves did not exist yet at that earliest moment. What existed was a hot plasma of quarks, gluons, and radiation. The particles that would eventually settle into the protons and neutrons of your body were mingling with the particles that would eventually settle into the most distant galaxy we can see. They were not neighbors. They were not close. They were together. Here is the strange part. That shared origin leaves a fingerprint. When two physical systems are in thermal contact, they equalize. Their temperatures match. Their properties correlate. And when they are later pulled apart, those correlations do not simply vanish. They persist, encoded in statistics, in patterns, in the very uniformity of the universe we see today. When astronomers look at the oldest light in the sky, light that has been traveling for nearly 14 billion years, they find something remarkable. Its temperature is almost exactly the same in every direction, to about 1 part in 100,000. A region of sky on your left matches a region of sky on your right, even though those two regions are now so far apart that light has never had time to travel between them since the universe began. How can two regions that never communicated look identical? They look identical because they were once the same region. They were in contact, and that contact is the first thread in the web we're about to follow. The next thread is the light itself, and where it has been. There is a glow filling the entire sky. You cannot see it with your eyes. It is too cool, too stretched, too old. But if you had eyes that could detect microwaves, the night sky would not be dark. It would be uniformly bright in every direction. Softly, faintly, but everywhere. This glow is called the cosmic microwave background, and it is the single most important piece of evidence connecting you to the deepest past of the universe. Here is what it actually is. For the first 380,000 years after the Big Bang, the universe was too hot for atoms to form. Protons and electrons flew around as free particles, and light could not travel in a straight line. Every photon bounced off an electron within a tiny distance, the way light bounces inside a thick fog. The entire universe was opaque, glowing, hot, and blind. Then the universe cooled. When the temperature dropped to about 5,000 degrees Fahrenheit, protons and electrons could finally pair up into neutral hydrogen atoms. The fog lifted. For the first time in cosmic history, light could travel freely. That first wave of freed light is still traveling, right now, hitting you. Think about what that means. Nearly 14 billion years ago, a photon somewhere out in what would become the deep cosmos finally broke loose from the plasma. It started flying. The universe kept expanding around it. Its wavelength got stretched. Its temperature cooled. For 14 billion years it travelled, and then today it ended its journey inside your television antenna, or a radio telescope, or the tissue of your hand. A small percentage of the static you used to see on old analog televisions was this light. The same light that witnessed the universe become transparent, landing in your living room. Now hold on to something, because this is where the connection becomes personal. When that photon was released, the matter that would become you was also sitting in that hot plasma. You were there, in ingredient form, as a bundle of protons and electrons and deep cosmological possibility. The photon and the proto-you parted ways at the same moment. The photon went one direction, your ingredients went another. For nearly 14 billion years, those ingredients drifted, clumped, formed stars, exploded, reformed, eventually became a planet, then became you. And all that time the photon was travelling. Today you and the photon meet again. You are, in a very real sense, two children of the same instant reunited, and this light is not rare. Roughly 400 photons of the cosmic microwave background pass through every cubic centimetre of space, right now, everywhere. Your body is being gently rained on by the oldest light in existence. Tens of millions of these ancient photons pass through you every second. This is not a metaphor, it is a physical fact. You are being bathed in the afterglow of the beginning. But here is the puzzle. When we measure this light from different directions, it all has the same temperature. Regions separated by vast cosmic distances, regions that should never have touched, are wearing matching uniforms. Something must have connected them before they drifted apart. Something earlier, deeper, stranger than the light itself. Point a telescope at the northern sky, count galaxies, measure their temperatures, their chemistry, their distribution. Now point the same telescope at the southern sky. Do the same. The results match. Not approximately, precisely. Zoom out to the larger scales we can measure, and the universe looks the same in every direction we point. Astronomers call this property isotropy, and at first glance it sounds like a comforting fact. A tidy universe, a well-organized cosmos. Except, when you think about it carefully, it should be impossible. Here is why. The universe is about 14 billion years old. Light travels at a fixed speed. That means the farthest anything can have communicated with anything else in the entire history of the cosmos is 14 billion light years. No signal, no heat exchange, no physical influence of any kind can travel faster than light. This is a hard limit, not a technological one. Now imagine 2 points in the sky, one far to your left, one far to your right. Each is near the edge of what we can see. The distance between them, measured across the sky, is far greater than 14 billion light years. These 2 points have never been in contact. Light has never had time to cross from one to the other. They are, in the language of physics, causally disconnected. They live in separate information bubbles that have never overlapped. By every rule we know, they should look different. If you drop a hot stone into one corner of a pond, and a cold stone into another corner, and you check the water temperature an hour later, the corners will match only if the water has had time to mix. If it has not, the corners stay different. Information, in the form of heat, needs a path. The 2 edges of our observable universe have no such path. They have not mixed. They have not shared a single photon with each other since the beginning of time, and yet their temperatures agree to 1 part in 100,000. This is called the horizon problem. It is one of the deepest puzzles in modern cosmology, and it bothered physicists for decades. How can 2 regions that cannot possibly have communicated end up identical? Is it a coincidence? Did the universe just happen to start out perfectly uniform everywhere, for no reason? That answer was unsatisfying, because a universe where 2 isolated regions randomly match to 5 decimal places is a universe that looks engineered, and physicists do not like unexplained engineering. There had to be a mechanism. Something in the early universe must have placed these distant regions in contact, letting them equalize, and then separated them so thoroughly that they now sit beyond each other's horizons. The proposed mechanism is called inflation, and it is the most radical, most speculative, and most successful idea in modern cosmology. It says that in the first tiny fraction of a second after the Big Bang, the universe did not expand smoothly. It inflated violently, exponentially, doubling in size, then doubling again and again, dozens of times over, in less time than it takes light to cross a proton. Regions that were once touching got flung to opposite ends of what would become our observable universe. Their matching temperatures are a fossil of an earlier intimacy. We have to look at what inflation actually did, because it is the reason everything you see in every direction is related to you. A physicist named Alan Guth, working late one night in 1979, scribbled the word spectacular in his notebook. He had just realized that if the very early universe went through a brief period of exponential expansion, every puzzle in cosmology would dissolve at once. The horizon problem, the flatness of space, the absence of exotic leftover particles, all of it. The idea he wrote down is called inflation. Let me walk you through what it actually claims, because once you see it, the connection between you and the farthest galaxies becomes almost tangible. Imagine the universe at an age of 10 to the minus 36 seconds. That is a 1 preceded by 35 zeros and a decimal point, then a 1. A number so small that calling it a fraction of a second insults fractions. At this moment, the universe is smaller than a proton, incredibly hot, and filled with a strange kind of energy that physicists call a false vacuum. The false vacuum has a peculiar property. It pushes outward. Unlike ordinary matter, which attracts itself through gravity, this energy repels itself. It wants to grow. It wants to make more of itself, and it does. Once inflation started, the universe doubled in size in an almost unimaginably short time, then doubled again and again. In the span of about 10 to the minus 32 seconds, the universe underwent at least 60 doublings, possibly many more. 60 doublings. Take a moment with that number. If you start with a penny and double it 60 times, you end up with more money than exists on Earth. The universe did the same, except with space itself. A region that started smaller than an atom ended up larger than a grapefruit, and then, crucially, it kept expanding, though more slowly, for the next 14 billion years, becoming everything we see. Here is what that explains. Before inflation, the tiny patch that would become our observable universe was small enough for every point inside it to be in thermal contact with every other point. Heat mixed, properties equalized, everything homogenized. It was physically one connected system. Then inflation ripped that patch apart. What were neighboring regions got hurled to positions that are now billions of light years apart. They carried their matching temperatures with them, like twins separated at birth who still share the same fingerprints. This is why the sky looks uniform in every direction. Every region you see, no matter how far, was once in intimate physical contact with every other region. Inflation did not create the uniformity. It preserved it and stretched it across the cosmos. And this stretching did something else, something even more remarkable. Tiny quantum fluctuations, the little jitters that always exist in any quantum field, got stretched along with everything else. Those microscopic jitters became cosmic scale ripples. Those ripples became the seeds of galaxies. The arrangement of galaxies you see when you look up at the night sky is a magnified photograph of quantum noise from the first trillionth of a trillionth of a trillionth of a second. Every star you can see traces its position to a random quantum wiggle in a region that was once pressed against the region that would become you. This is the real meaning of inflation. It is not only that the universe got big, it is that the seeds of everything, including you, including every galaxy, were planted in a shared, intimate quantum moment. And the rules of that moment still govern what can reach you now. Physics has a concept that sounds simple until you sit with it for a while. It is called causal contact. 2 points in space are in causal contact if a signal, travelling no faster than light, could have passed between them at some point in their shared history. If such a signal could exist, the 2 points can influence each other. If it could not, they are, for all practical purposes, in separate universes. Now here is the strange consequence. Once 2 points have been in causal contact, they are never truly independent again. Think of it like handshakes across a dance floor. If you have shaken hands with someone at some point in the evening, a trace of that encounter remains, at least in memory. The two of you share information. You know something about each other. You might drift to opposite corners of the room and never speak again, but the handshake happened. It is part of both of your histories. The universe works the same way, except the memory is not emotional. It is physical. When 2 regions of space were in thermal contact in the early universe, they exchanged photons, particles, and energy. They reached common values of temperature and density. Their properties correlated. When they later separated, dragged apart by expansion, they carried those correlations with them. A careful measurement today can detect the matching. This is how cosmologists read the early universe. They are not watching it directly. They are reading the correlations left behind in the cosmic microwave background, in the distribution of galaxies, in the chemistry of ancient stars. The universe is a vast archive of handshakes, and modern physics is learning to read them. But here is where it gets beautiful. You and a distant galaxy cluster are in causal contact, right now, in a specific and measurable sense. The galaxy cluster's light has reached you. Photons born in its stars have travelled across cosmic distances, has landed on your skin, on your telescope, on your retina. That is one-way causal contact. They have influenced you. Have you influenced them? That depends on how far away they are and how old the universe is. If they are close enough and enough time has passed, yes. Light you emitted yesterday is travelling toward them right now, and in some future billion years it will arrive. In the grand accounting of the cosmos, you are sending messages you will never see received. But there is a limit. As the universe expands, some regions are accelerating away from us so fast that light leaving Earth today will never reach them. They were in our past. They will not be in our future. The handshake has ended. Physicists call this the cosmic event horizon. It is a boundary, but not one you could ever approach. It is the boundary of what you can still affect. Everything inside it you are still in contact with. Everything outside it you have lost forever. Within your horizon, though, every single point is something you share a history with. Every galaxy, every cloud, every speck of dust has been part of a causal web that includes you. The universe you can see is not a collection of strangers. It is a family separated by distance, connected by a past none of us can remember, but all of us inherit. The shape of that connection, the actual geometry of it, is our next puzzle. Here is a question that sounds simple and turns out not to be. How big is the universe? The honest answer is that we do not know. The universe might be infinite. It might be vastly larger than what we can see, but finite. It might curve back on itself in ways we have not detected. What we can measure with precision is the size of our observable universe. And that measurement leads to one of the strangest mental pictures in all of cosmology. The observable universe is a sphere centered on you, not centered on Earth, or the Sun, or the Milky Way. On you, the person you are. Right now, reading this, the center of your personal observable universe is exactly where your eyes are. Someone on a planet in the Andromeda Galaxy has a different observable universe centered on them. It overlaps enormously with yours, but it is not the same sphere. An alien astronomer in a galaxy 10 billion light-years from here has an observable universe centered on their telescope, and their sphere extends into regions you have never seen and never will. There is no privileged location. Everyone is at the center of their own sphere. The radius of our sphere is about 46 billion light-years. That number surprises people. Our universe is about 14 billion years old, so how can we see things 46 billion light-years away? Should not the limit be 14? The answer lies in expansion. When light left the most distant galaxies we can see, those galaxies were much closer to us. They've been riding the expanding space outward ever since, while their light travelled toward us through that same expanding space. By the time the light arrived, the galaxy had drifted much farther. The light left from close-up. The source is now far away. This means our observable universe contains galaxies whose current position no light signal could ever reach again. We see them as they were, not as they are. We have photographs of distant pasts, not portraits of distant presents. But here is the key insight for our story. Every point inside this bubble, no matter how far, shares a history with you. Every galaxy inside your sphere was once, at the beginning, in causal contact with the matter that would become your body. Your observable universe is defined as the set of points that have been able to influence you since the Big Bang. By definition, every one of those points is linked to you. When you look out, you're looking into your own past, literally. A galaxy 5 billion light-years away appears as it was 5 billion years ago, before the Earth even existed. You're looking at your ancestor universe, back when your atoms were still churning inside dying stars in a much closer volume. And because the universe keeps expanding, your observable sphere is slowly losing galaxies at its edge. They are drifting out of it, beyond the horizon, into regions you can no longer affect or be affected by. Right now, as you read this, galaxies are crossing that invisible boundary. Their final light, the last messages they will ever send you, is arriving. Tomorrow, more will leave. This is happening every second. You're the center of a bubble that is slowly shrinking in membership, even as it grows in size. The structure of that bubble, and the paths light takes through it, is our next subject. Physicists have a tool for thinking about space and time together. It is called a light cone, and once you understand it, the connection between you and the rest of the universe becomes almost visible. Start with this picture. You're standing at a single moment, here and now. Time goes upward on our mental diagram. Space spreads out to the sides. Any event anywhere in the universe can be placed somewhere on this map. Now, draw all the places a beam of light could reach if you emitted one right now. That beam travels outward at the speed of light, covering more and more space as time goes on. The set of all points your light could touch forms a cone, opening upward into the future. This is your future light cone. Everything inside it is something you might one day influence. Now draw the cone going backward. The set of all places in the past from which light could have reached you by now, that is your past light cone. Everything inside it is something that could have influenced you. Here is the remarkable part. Your past light cone does not contain just a few events. It contains every photon that has ever reached your eyes, every gravitational wave that has wrinkled the space around you, every cosmic ray that has pierced your cells, going all the way back to the moment the universe became transparent. Your past light cone is a vast, upside-down, time-spanning structure. It is shaped like a cone when the universe is static, but in our expanding universe it curves. Its walls bend inward in the deep past because the universe was smaller then. Near the beginning, your past light cone nearly pinches to a point. What this means is profound. Every object in your observable universe sits inside your past light cone. Every star you've ever seen, every galaxy ever photographed, every photon of the cosmic microwave background. All of them are events that light has traced a path from to arrive now, at you. They are not just in your sky, they are in your past. Think about what this does to the word here. When you stand somewhere, your here is not a point in space. It is the tip of a cosmic cone reaching back through all of time, gathering in everything that has ever touched you by light or gravity or particle. Your here is the convergence point of a universe's worth of history, and here is where the philosophical weight lands. You're not a passive observer of the cosmos. You're a terminus. You're the place where the universe's light finally stops and gets registered. Every photon that strikes your retina completes a journey that began in the hot heart of a star, possibly before Earth existed. That journey ends inside you. You are the final word of a story that took billions of years to tell. Now double that picture. Imagine every observer in the universe has their own past light cone, gathering in their own slice of history. All these cones interweave and overlap. The cosmos is a mesh of light cones, each one a different perspective on a shared history. You're not alone in the center of your bubble. You are one node in an infinite network of nodes, each one reading its own handshake record from the same early universe. And the oldest handshakes in your record, the ones closest to the big beginning, are still arriving as photons on your skin. Let us make the invisible visible for a moment. Step outside at night. Look up. Hold out your hand, palm facing the sky. Do not move it for a full minute. In that minute, somewhere between 100 million and 1 billion photons of starlight will strike the surface of your palm, some from nearby stars a few dozen light years away, some from stars on the far side of our galaxy, 30,000 light years away, and a scattering of them, a small but real fraction, from galaxies so distant that their light has been travelling toward you for billions of years. The farthest photons you can see with the naked eye come from the Andromeda Galaxy. They are about 2.5 million years old. The light entering your pupil tonight left Andromeda before our human ancestors had figured out how to make stone tools. It has been travelling, unblinking, through the vacuum for the entire duration of the human story, only to end in the back of your eye. With a small telescope, you can see light from galaxies tens of millions of years old. With a good observatory, billions, and with the cosmic microwave background, the limit is nearly 14 billion. Here is something most people never picture clearly. Light does not weaken by being old. A photon that has travelled for 12 billion years carries the same energy per quantum as a photon emitted last Tuesday, minus only the stretching caused by cosmic expansion. When it arrives at your skin, it deposits that energy just as a new photon would. It warms the outermost atoms of you by an immeasurably tiny amount, and then it is gone. Your body is being warmed, right now, by the collective energy of trillions of photons from thousands of galaxies. Most of it is far too faint for you to notice. Your skin cannot tell a photon from Andromeda from a photon from the streetlight next door. But the physics does not care about your ability to notice. The photons arrive, the energy deposits, the interaction is real. Let me give you a concrete number. The surface of your body is being struck every second by roughly 10,000 cosmic microwave background photons per square centimetre. Over the area of a human body, that is hundreds of millions of primordial photons per second landing on you. Every second. While you sleep, while you eat, while you read. Each one is a message from a specific patch of the very early universe. Each one carries information about the density, the temperature, and the quantum fluctuations of its birthplace. Collectively, they encode the most detailed map we have of the infant cosmos, and a tiny, tiny fraction of those photons are coming from a patch of the early universe that is causally related to the patch that would become your body. In the first fraction of a second before inflation separated them, the place the photon came from and the place where your atoms were being assembled were neighbours, closer than neighbours, part of the same hot mixture. So when one of those photons lands on your skin, there's a real sense in which a piece of your ancient neighbourhood is coming home to you. The universe is not an abstract backdrop. It is a shower of continuous arrivals, old light meeting old matter, separated siblings, reunited for a single instant. The matter itself, the atoms making up your body, has its own stranger journey to tell. Take a glass of water. Look at it. Roughly 2/3 of the atoms in that glass are hydrogen. Every hydrogen atom consists of a single proton, sometimes paired with an electron. Those protons are almost 14 billion years old. This is not an exaggeration. It is not a metaphor. The protons in the hydrogen of your water, the hydrogen in your blood, the hydrogen in every molecule of every living thing on Earth, were formed during a period that lasted roughly 3 minutes, a long time ago, when the universe was a hot bath of quarks and gluons and radiation cooling rapidly from its initial fury. This period is called Big Bang nucleosynthesis, and it is one of the most elegant confirmations of modern cosmology. Here is what happened. Just after inflation ended, the universe was a fiery plasma, too hot even for protons and neutrons to exist as stable particles. As it cooled, quarks began binding together to form protons and neutrons. Most settled into protons, the simple kind with one quark configuration. A smaller number became neutrons. Then came a critical window. For about 3 minutes, the universe was cool enough for protons and neutrons to stick together, but still hot enough to fuse them into heavier nuclei. Some protons and neutrons combined to form deuterium, a heavy kind of hydrogen. Some deuterium combined further to form helium. A tiny amount of lithium formed, and then the universe cooled below the temperature where fusion could continue, and the composition of primordial matter was frozen in. When the dust settled, the universe was about 75% hydrogen, 25% helium, and a trace of lithium. That ratio has barely changed since. The hydrogen in your body is that hydrogen. Every proton in every water molecule in your veins was created in those 3 minutes. It has been recycled through stars, floated in interstellar clouds, become part of planets, been drunk by dinosaurs, evaporated into rain, filtered through roots, and ended up inside you. But it has not been destroyed. Protons are remarkably stable. Their half-life, if they decay at all, is longer than the age of the universe by many orders of magnitude, which means something strange when you think about it. You're drinking a glass of nearly 14 billion-year-old water. The atoms are older than the Earth, older than the Sun, older than our galaxy. The only reason they're here in a glass, on a table, in a room where you sit, is that the universe spent nearly 14 billion years moving them through its own history, slowly, patiently, until they found their way into the living thing that is you. And here is the connection to the broader universe. The hydrogen in your body did not form in isolation. It formed in a vast universal process that happened everywhere at once. Every star you see in the sky is also made mostly of primordial hydrogen. Every gas cloud between galaxies. Every water molecule anywhere in the observable universe. This means your body shares a physical ingredient, in the most literal sense, with every other body of matter in the cosmos. We are all made in large part from the same 3-minute batch of cooking, but the heavier ingredients, the carbon, the oxygen, the iron, those have a more violent origin. The hydrogen is old, it is everywhere, but you're not mostly hydrogen by mass. You're mostly carbon and oxygen, with nitrogen, phosphorus, calcium, iron, and a host of other elements. None of these existed in appreciable amounts when the universe was 3 minutes old. So where did they come from? They came from stars, specifically from stars that were born, lived out their lives, and died before our solar system formed. Those stars are gone, their remnants are scattered, but the atoms they made are still here, in you. Here is how it worked. When the early universe cooled, the primordial hydrogen and helium began to clump under gravity. Eventually, clumps became dense enough to ignite nuclear fusion at their centers. The first stars were born. These first stars were monsters, far larger than our sun, far hotter and far shorter lived. A star like our sun lives for about 10 billion years. The first generation of stars lived for only a few million. Inside their cores, these stars performed nuclear alchemy. They took hydrogen nuclei and smashed them into helium, then they smashed helium into carbon, then carbon into oxygen, then oxygen into neon, silicon, sulfur, and eventually iron. Layer by layer, like an onion, the star built up heavier and heavier elements. When such a star ran out of fuel at the centre, It could no longer hold itself up against gravity. It collapsed, and the collapse triggered an explosion of staggering violence called a supernova that ejected all those carefully built-up elements into space. A single supernova can outshine an entire galaxy for weeks. It can scatter its contents across vast distances. And it does something special in those final moments. The shockwave of the explosion compresses and fuses materials so rapidly that it creates elements even heavier than iron. Gold, silver, uranium. Every atom of gold on Earth was made in a stellar explosion, possibly in the merger of two dead stars long before our sun existed. Now consider where you stand on this timeline. Our sun formed about 4.5 billion years ago from a cloud of gas and dust that had been seeded by multiple previous generations of stars. That cloud contained hydrogen and helium from the Big Bang, mixed with carbon from old red giants, oxygen from dying blue stars, iron from supernovae, and gold from colliding neutron stars. All of these ingredients were swirled together in a great interstellar nursery, compressed by a nearby shock wave, and collapsed into the disk that would become our solar system. The carbon in your DNA, the oxygen you breathe, the iron in your hemoglobin, the calcium in your bones, each of these atoms was forged in a specific star somewhere in our galaxy, at a specific moment, possibly billions of years before the Earth even existed. You are quite literally a reassembly of dead stars, a walking supernova echo. And this is not just a local story. Every solid planet in the universe, every ocean, every living thing wherever it exists, is built from the same kind of process. Stars all across the cosmos are still doing this work, forging heavy elements and scattering them. Somewhere out there, right now, a supernova is making atoms that will, in some far future, become part of a thinking being. The universe is not just connected by light and expansion. It is connected by an ongoing process of making, using, and remaking matter. The scale of that process is our next chapter. Stand still for a moment and try to picture this. Inside your body right now, there are atoms that were manufactured in at least several different stars. Not one, several. The iron in your blood did not all come from the same supernova. Some came from one dying giant, some from another. The carbon in your fingernails was assembled over many stellar lifetimes, blended by the slow churning of galactic gas clouds. Your body is a composite, a mosaic of atoms from an unknown number of cosmic factories. This mixing process, the slow churn of dead stellar material into the raw matter of new stars and planets, is called galactic chemical evolution. It is how a galaxy builds up, over billions of years, the ingredients needed for complex chemistry and eventually for life. Let me give you a sense of the scale. Our galaxy, the Milky Way, contains somewhere between 100 billion and 400 billion stars. Roughly one supernova explodes in our galaxy every century. Over the 13 billion year history of the Milky Way, that is around 130 million supernova explosions. Each one has seeded the galaxy with heavy elements. Each one has contributed in some tiny way to the raw material that became our sun, our Earth, and you. The atoms in your body are statistically the product of thousands of stellar deaths. Not all from the same region, not all from the same era. The iron in your left pinky finger might have been synthesized in a star that exploded on the other side of the galaxy 8 billion years ago. The iron in your right pinky might have come from a different star much closer to our current position that exploded only 1 billion years ago. You are carrying pieces of a galactic patchwork, and the stars that contributed to you are in many cases not even in the same location as they were when they exploded. Stars orbit the galactic center. They drift. The cloud of debris from a supernova spreads out, gets pulled by gravity, mixes into the general interstellar medium, and over time becomes essentially homogeneous at the scale of a star-forming region. By the time a new star forms from this gas, it has ingredients from countless older stars thoroughly blended. You are, in this sense, a sample of the Milky Way, a small, portable, breathing sample of the chemistry of our entire galaxy. If an astronomer on a distant planet could somehow analyze you, atom by atom, they could reconstruct much of the chemical history of the Milky Way from your body alone. But it does not stop there. The Milky Way is itself connected to other galaxies. Gas flows between galaxies in a diffuse, nearly invisible cosmic medium. Galaxies collide and merge. Our own galaxy has absorbed at least a dozen smaller galaxies over its history, and it is slowly being tugged toward Andromeda right now. Every collision mixes material. Every absorption adds new atoms to the galactic inventory. There is a real possibility that some atoms in your body came originally from a star that was born in a different galaxy, one that was later swallowed by the Milky Way billions of years before Earth formed. The ingredient list of a human being is not local, it is cosmic. It draws from a volume of the universe much larger than just our galaxy. And all of this mixing, all of this sharing of atoms, happens under the same set of physical laws, the same laws that operate on the other side of the observable universe. That universality of law is our next thread. This is one of those facts that is so familiar, we almost forget to be amazed by it. The laws of physics that govern a cup of coffee on your kitchen table are exactly the same laws that govern the atoms in a galaxy 2.5 million light-years away. Exactly the same. This might sound obvious, but there is no logical reason it has to be true. You could imagine a universe where gravity worked differently on the other side of the Milky Way, or where the charge of the electron changed with position, or where the speed of light varied from one galaxy to another. Such universes are perfectly conceivable, they are just not ours. Our universe appears to have uniform physical laws across every location we can observe, as far as we can measure. This property is so reliable that astronomers use it as a tool. When an astronomer wants to know what a distant star is made of, they do not travel to it. They cannot. Even the fastest spacecraft we have built would take tens of thousands of years to reach the nearest star, and that is just one star, a neighbour. Instead, they collect a little light from it and spread that light into a spectrum, like a rainbow. They look at the pattern of dark lines in that spectrum. Hydrogen in a lab on Earth absorbs light at specific wavelengths. Very specific. The pattern is like a fingerprint. When they look at the spectrum of a star, they see the same fingerprint. Shifted a bit, perhaps, by the motion of the star, but unmistakably the same pattern of lines. This means the hydrogen in that distant star is behaving exactly like the hydrogen on Earth. We have done this for stars tens of millions of light years away. The results always match. Hydrogen is hydrogen wherever it is. Helium is helium. Iron is iron. The chemistry, the nuclear physics, the quantum mechanics, all of it holds. This extends even to the farthest galaxies we can see, whose light has been travelling for more than 12 billion years. When we decode their spectra, we find the same elements, the same atomic transitions, the same rules. The universe, in every direction we can look, obeys a single, unified rulebook. This is not a small fact. It means that your understanding of how things work, built from experiments in laboratories on Earth, is applicable to the entire observable cosmos. The equations you scrawl on paper describe galaxies you will never touch. A chemist's intuitions about water molecules are valid on a planet you will never see, and it means something deeper about connection. If every region of the universe were governed by different rules, it would be as though the different parts were genuinely separate realms, each with its own customs, unable to really share anything fundamental, but they all obey the same rules. A hydrogen atom here and a hydrogen atom in a galaxy 10 billion light-years away are, in their deepest nature, identical, not similar, identical. They are instances of the same pattern. This hints at something physicists have been puzzling over for a century. What is it that makes all these electrons, all across the cosmos, behave exactly alike? Why do they all have the same mass, the same charge, the same behaviour? The answer, when you dig deep enough, is stranger than anyone expected. They might in a sense all be the same thing. We are approaching that idea now. There is a number in physics that has no known explanation. It is not derived from any deeper theory. It is not predicted by any model. It is simply measured, and yet, without it being exactly what it is, the universe as we know it could not exist. It is called the fine structure constant. Its value is approximately 1 divided by 137. This number describes the strength of the electromagnetic interaction. It determines how strongly charged particles, like electrons and protons, pull on each other. It shapes the size and structure of atoms. It controls how light interacts with matter. In a sense, it is the dial that sets how tightly the electromagnetic force grips the universe. If the fine structure constant were slightly larger, electrons would bind so tightly to nuclei that chemistry as we know it would fail. Molecules like water and DNA would not form in any useful way. If it were slightly smaller, atoms would be so loosely bound that matter could not hold together under the conditions of a living planet. In either case, no use. We exist because this number is what it is, not because the universe was designed for us, but because we are a phenomenon that only arose because this dial happened to be set in the narrow range where complex chemistry works. Here is the connection point. The fine structure constant is the same everywhere we have measured it. In your body, in the rocks of the moon, in the atmosphere of the sun, in the plasma of distant quasars, whose light we observe from 12 billion years in the past. The same value. Physicists have looked hard for variation. They have compared the spectra of hydrogen atoms here with the spectra of hydrogen atoms in ancient galaxies. They have checked whether the fine structure constant might have been different in the early universe. The answer, within our best measurements, is no. It has held the same value everywhere at all times for nearly 14 billion years. This kind of universality is what allows physics to exist as a science. If the constants changed from place to place, there would be no laws, only patches. There would be no way to predict anything outside your immediate neighbourhood. But they do not change. They hold. They are constant across the entire sweep of the cosmos, and that fact tells us something about the nature of reality. These constants are not properties of individual objects, they are properties of the universe itself. They describe the stage on which everything happens, not the actors. The stage is the same from one side of the observable universe to the other. When you touch a table, the electromagnetic force between the electrons in your fingertips and the electrons in the table is governed by the fine structure constant. When light from a distant galaxy scatters off an electron in a quasar, the strength of that scattering is governed by the same fine structure constant. You and that quasar are playing on the same field. With the same rules, with the same dial settings, there is no secret quasar physics that differs from kitchen physics, and this leads to a question that unsettled physicists for much of the 20th century. If all electrons behave identically to an exquisite precision, what actually makes them so alike? Is it just coincidence? Or is there something deeper, something that unifies them? There is an idea that every electron in the universe might be, in some strange sense, the same electron. It sounds absurd. It also solves the puzzle elegantly, and it leads us directly into the territory of quantum entanglement. Let me set up a specific thought experiment. We will use it for the next few chapters because entanglement is one of the strangest and most misunderstood ideas in all of physics, and the only way to see it clearly is step by step. Imagine you have a machine that produces pairs of particles, a photon here, a photon there. The machine makes them in such a way that a particular property, call it their polarization, is shared between them in a specific way. The details of how the machine works do not matter. What matters is the outcome. You take one of the photons and fly it to a lab in New York. You take the other and fly it to a lab in Tokyo. Two particles, one 35,000 miles apart from the other, more or less. They have no string between them, no signal connecting them. They are, in every classical sense, isolated. Now you run an experiment. In both labs, at the same moment, you measure the polarization of the photon. Each measurement has two possible outcomes. Let us call them up and down. Here is what the machine guarantees. When the two photons are made a specific way, the outcomes will always be correlated. If New York gets up, Tokyo gets down. If New York gets down, Tokyo gets up. Every single time, across thousands of trials, the correlation is perfect. Now there is a simple way this could happen. You could imagine that each photon secretly carries a hidden label. One is labelled "I will be up when measured." The other is labelled "I will be down when measured." They were assigned these labels at the moment they were created, and they carry the labels to New York and Tokyo respectively. When measured, they simply reveal their pre-assigned values. No mystery, no spooky connection. This was Einstein's preferred interpretation. He believed that quantum mechanics was simply an incomplete theory, and that underneath it were hidden variables that determined outcomes in advance. For decades, this seemed like a reasonable possibility. There was no way to experimentally test whether the photons had pre-assigned labels or whether something stranger was happening. And then a physicist named John Bell in 1964 did something brilliant. He wrote down a mathematical inequality that any theory with hidden pre-assigned labels would have to satisfy. It was a constraint on the statistics of correlations testable in a laboratory. If the photons carried hidden labels, the statistics would stay within certain bounds. If something else was happening, the statistics could exceed those bounds. The inequality was named after him. The experiments took another few decades to refine, but by the 1980s physicists had performed them carefully, and the results were clear. Bell's inequality was violated. The statistics exceeded what any hidden label theory could produce, strongly, unmistakably, repeatedly. The photons were not carrying pre-assigned labels. Their outcomes were genuinely not determined until the moment of measurement, and yet when both were measured, their outcomes still correlated perfectly across thousands of miles of separation. This is entanglement, not a trick, not a clever correlation set up in advance, a genuine, measured, laboratory-confirmed phenomenon in which two particles share a single quantum state even when they are far apart, and the state resolves into definite values only when either one is measured, in a way that affects both at once. Something is connecting those photons. Something that does not respect distance in the ordinary sense. We need to understand what that something is and what it is not. Bell's theorem is worth slowing down for, because it is the moment physics had to admit that the world is stranger than our everyday experience suggests. Imagine you and a friend play a game. Each of you gets a sealed envelope. You agree that inside each envelope is a card, either red or blue. You will open the envelopes in different cities and compare results. If every time one of you gets red, the other gets blue, you would naturally conclude that the cards were decided in advance. At the time the envelopes were sealed. No magic, just a prearrangement. That is the intuition Einstein wanted to apply to entangled particles. The outcomes are correlated because they were decided at the source, back when the particles were created together. The particles carry their secret answers with them and reveal them on demand. Bell looked closer. He noticed that in quantum mechanics, the two observers can choose different questions to ask. Not just what color is the card, but any of several possible measurements, chosen independently at each location. The observer in New York can decide at the last moment which measurement to perform. The observer in Tokyo can decide separately. Bell worked out what the statistics of their results should look like if the particles carry pre-assigned answers. If each particle has a hidden list of what it will do for every possible measurement, then the correlations between the two observers must obey a specific inequality. No hidden list theory, no matter how clever, can produce correlations stronger than this. Quantum mechanics predicts stronger correlations, in some configurations dramatically stronger. The experiments, beginning with Alain Aspect in the 1980s and refined ever since, have confirmed the quantum predictions over and over. The correlations exceed Bell's bound. The particles cannot have been carrying pre-assigned answers. This is worth pausing on. It is not that the experiments were inconclusive. It is not that physicists think hidden variables are unlikely. The experiments show, as clearly as any experiment shows anything, that no theory of local pre-assigned properties can account for what we measure. Nature does not work that way. So what does that leave us with? It leaves us with two options, and either is strange. One option is that the particles are genuinely connected in a way that does not respect distance. When you measure one, the state of the other responds somehow, even if they are on opposite sides of the galaxy. This connection is not a signal, because it cannot be used to send information faster than light. But it is a correlation that requires something to link the two particles beyond ordinary cause and effect. The other option is to give up on the idea that physical properties have definite values before they are measured. In this view, the particles genuinely have no properties of their own until an observation happens. The act of measurement creates the values on both sides, simultaneously, across any distance. Most physicists today accept some version of this second view, often blended with pieces of the first. The technical name for the framework is the non-locality of quantum mechanics. Non-local does not mean telepathic or supernatural. It means that the simple picture of objects sitting in space, each with their own local properties, is incomplete. The universe at the quantum level is knit together in a way that our intuitions about separate things sitting in separate places cannot capture. This is not philosophy, it is experimental fact, and it has implications for how connected we really are to the rest of the universe. Here is where people often get excited and then a little disappointed. When they learn about entanglement, they sometimes think it means we can send messages faster than light, across the galaxy, instantaneously, a quantum telephone to another world. Unfortunately for science fiction, this is not possible. The reason is subtle but important. when you measure one of the entangled particles, you get a random result. If the measurement is set up so that the outcome is either up or down, you get one of those two outcomes with 50-50 probability. The randomness is genuine. You cannot control it. You cannot choose to get up rather than down. The particle in the other lab also gives a result, and it is correlated with yours. If you got up, they got down. But they also see a random-looking result on their end. They get 50-50 statistics too. There is no way for them to know from their results alone that anything unusual has happened. The correlation only becomes visible when the two observers compare their results later through ordinary means of communication, over a phone line or the internet or a radio signal, and those means are limited by the speed of light. So entanglement as a method of communication is useless. You cannot use it to send information faster than light. The universe has built in a safeguard against that. But do not let that fool you into thinking entanglement is trivial. It is not a communication channel, but it is a connection. The two particles are genuinely linked in a way that produces statistical agreements no classical theory can explain. Their randomness is correlated, their destinies are tied. And here is what is important for our larger story. Entanglement is not a special trick that happens only in laboratories with precise equipment. It is a baseline feature of the quantum world. Whenever particles interact, they tend to become entangled. Whenever two systems touch, even briefly, they typically share some quantum correlations afterward. Think about what that means for a universe whose entire contents were once in direct contact in that initial hot, dense state before inflation. Every particle that will ever exist in your body interacted at some point with every particle that will ever exist anywhere in the observable universe. They shared quantum states. They became, at least in principle, entangled. That entanglement did not disappear when they flew apart. Some of it has decohered, meaning the correlations have been scrambled by subsequent interactions with other particles until they are functionally untraceable, but not all of it. Some residual entanglement remains in principle between particles in you and particles in the farthest galaxies you can see. This is a theoretical point, and it is hard to measure. The entanglement that survives is usually buried under so much noise that experimental detection is impossible. But the point is this: entanglement is not rare. It is the default. It is what happens whenever quantum systems interact. And the early universe was one big interacting quantum system. You're not a separate node in a disconnected network. You're a knot in a tangled thread that runs through all of space and time. The thread is faint in most places, but the threadedness itself is real. And that thread was not woven randomly. It was woven at the beginning when everything was one. Let us put the pieces together. The universe began in a single, hot, dense state. Every particle that existed then was in contact with every other particle. They interacted. They exchanged energy. They formed a single, coupled quantum system. And because quantum systems that interact become entangled, the early universe was a web of entanglement on a scale we can barely imagine. When inflation stretched space, those particles were flung to enormous distances. They did not stop being entangled. Entanglement does not care about distance. It is preserved by the laws of quantum mechanics, no matter how far apart the participants travel. So in principle, the matter in your body shares residual quantum entanglement with matter in a galaxy 10 billion light-years away. Both of you came from the same primordial soup. Both of you are in the same coupled quantum state. Some traces of that original entanglement survive in both of you, even now. This is sometimes called primordial entanglement. It is a real prediction of standard cosmology combined with standard quantum mechanics. Most physicists accept that it must exist, even though we cannot isolate and measure it directly. Why can we not measure it? Because of decoherence. When a particle interacts with its environment, it shares some of its quantum state with those surroundings. The original entanglement gets spread across many, many particles. What was once a clean correlation between two particles becomes a diffuse correlation among trillions. Extracting the original signal is hopeless with current technology, possibly hopeless in principle, but the entanglement is still there in a mathematical sense. It has been redistributed, not destroyed. Information, in quantum mechanics, is remarkably hard to truly destroy. It gets scrambled, it gets hidden, it very rarely disappears. This gives you a picture of the universe as a vast, mostly incomprehensible, but real quantum network. Every particle is correlated, however weakly, with an enormous number of other particles. Those correlations trace back to events in the deep past, to interactions that may have happened 14 billion years ago. When you take a deep breath, the oxygen molecules entering your lungs carry quantum correlations with matter across the cosmos. When a cell in your body splits and duplicates its DNA, the electrons participating in those bonds have histories that reach back to the first second of the universe and entanglement partners they have never lost. You're not a billiard ball, you're a knot in a net. The net was knitted in the first instant and it still holds. This framework leads to ideas that sit at the frontier of physics. What if entanglement is not just a correlation, but something more geometric? What if the reason two entangled particles share a state no matter how far apart is that they are connected through a structure we do not normally see? Some physicists have proposed exactly this. They suggest that entanglement, at its deepest level, is identical to a particular kind of geometric bridge through space-time, a wormhole, small and non-traversable, linking the two particles directly. If that idea is right, then the universe is woven together not just by history, not just by correlations, but by literal hidden threads of geometry. The network is a physical network, made of space itself. We are about to follow that thread. In 2013, two physicists named Juan Maldacena and Leonard Susskind proposed an idea that sounds like it belongs in a novel. They wrote a paper with a short cryptic title, ER equals EPR. The equation that was not really an equation. The proposal that, if true, would rewrite our understanding of what space actually is. Let me unpack what those letters mean. ER stands for Einstein and Rosen. In 1935, Albert Einstein and Nathan Rosen were studying the equations of general relativity, which describe gravity as the curving of space-time. They discovered a strange solution. Two black holes, far apart in ordinary space, could be connected through a hidden shortcut, a tube running through a deeper geometry. People later called these shortcuts wormholes, though the technical name is Einstein-Rosen bridges. These bridges were not traversable. You could not send a spaceship through one. They would pinch off before anything could cross. But mathematically they were there, allowed by the equations as geometric connections between otherwise separate regions. EPR stands for Einstein, Podolsky, and Rosen. The same Einstein, the same Rosen, plus Boris Podolsky. In a different paper, also in 1935, these three argued that quantum mechanics implied something absurd. Two particles, once they interacted, could remain correlated across any distance. This is entanglement, the same phenomenon we just explored. Einstein found it so disturbing he called it spooky action at a distance. He thought it proved that quantum mechanics was incomplete. For almost 80 years, nobody noticed the connection. 2 different papers, written by overlapping authors in the same year, describing 2 different strange phenomena. 2 black holes connected by a hidden bridge, 2 particles connected by a quantum correlation, seemingly unrelated. Then Maldacena and Susskind proposed something radical. What if they are the same thing? ER equals EPR. Every entangled pair of particles might be connected by a microscopic Einstein-Rosen bridge, a tiny, invisible wormhole linking them through a hidden layer of geometry. The reason measuring one affects the state of the other is not because of a signal passing through ordinary space. It is because, at a deeper level, they are already joined. The spookiness of quantum correlation and the strangeness of geometric shortcut are 2 faces of one reality. This is a conjecture, not a theorem. It has not been proven. It may turn out to be wrong or only partly right. But it has attracted enormous attention because it gestures at a unification between 2 pillars of physics that have resisted marriage for a century: quantum mechanics and general relativity, the very small and the very curved. If ER equals EPR is true, then every entangled particle in the universe is geometrically connected to its partner. And since primordial entanglement spans the cosmos, the universe is threaded with an invisible network of microscopic wormholes, not traversable, not useful for travel, but real, in the sense that the geometry of space-time itself is woven through them. You, then, would be connected to distant galaxies not only by photons arriving at your eyes and by shared history in the first instant, but by a web of tiny geometric bridges running beneath the visible layer of reality. This is speculative. It is at the frontier, where physicists are still arguing about interpretations, but it shows the direction the field is moving. Space itself might be built from entanglement. The fabric of the universe might be, at the deepest level, a network of quantum correlations that give rise to distance, to geometry, to the everyday sense of separation. If that is so, then space is not the background of connection. Space is the form connection takes. Pick any spot in your room where there is nothing, the air between your lamp and your window, the space just above your coffee cup. Look at it. That region is, by ordinary standards, empty. It is not. Even in the best vacuum physicists can create, better than the vacuum of deep space, there is still something there. That something is called the quantum vacuum, and it has a remarkable property. It is entangled with itself, everywhere, at every scale. Let me explain what that means. In quantum field theory, which is our most precise description of how nature works at small scales, empty space is not truly empty. It is the lowest energy state of a collection of fields that fill all of space. These fields are always humming, always fluctuating slightly, in ways that are dictated by the rules of quantum mechanics. The fluctuations cannot be eliminated. Even at absolute zero in the deepest vacuum, the jitter remains. Here is where it gets interesting. If you study the vacuum carefully, you find that the fluctuations in one tiny region are correlated with the fluctuations in nearby regions. The vacuum is not a collection of independent empty patches. It is a coherent, entangled whole. Small region A and small region B, sitting next to each other, share quantum correlations. Small region B and small region C share correlations. The whole vacuum is knit together. This is not a theoretical flourish. It has real, measurable consequences. The Casimir effect demonstrated in laboratories shows that 2 closely spaced metal plates in a vacuum are pushed together by the vacuum fluctuations themselves. This is possible only because the vacuum has structure. it has modes, it has correlations. The entanglement of the vacuum is strongest between neighbouring regions and weaker between distant ones, but it is present at every scale. If you carve the universe into small boxes, each box is entangled with its neighbours, and that entanglement forms a kind of woven fabric underneath what we call space. Some physicists believe this is the deepest clue we have to what space really is. In their view, the geometry of space is not fundamental. It emerges from the pattern of entanglement in the underlying quantum fields. Regions that are highly entangled with each other are, by definition, close. Regions with weak entanglement are far. Distance itself is a measure of how entangled two parts of the universe are. If this view is correct, then the statement "there is space between us" is a statement about our quantum correlations. The more entanglement that separates us, the more space fills the gap. This connects back to our journey. You and a galaxy billions of light years away are separated by an enormous amount of space. In this emerging picture, that separation is itself an expression of quantum entanglement patterns. The galaxy is not just far away, it is far because of the specific structure of the vacuum connecting you. The distance is made of entanglement, and within that distance the vacuum is continuously humming, fluctuating, and exchanging correlations. When you look up at the night sky, the light from that distant galaxy passes through a medium that is, at every point of its journey, quantumly stitched together. The photons are not travelling through a void. They're travelling through a living fabric, one whose threads reach from you to the galaxy and beyond. Empty space, in this light, is not a stage on which things happen. It is an active participant, a structure with its own properties, its own dynamics, its own web of connections. The fields that fill this fabric are the next thread to examine. We tend to think of the world as made of particles, little dots. Electrons, protons, photons, each a separate thing moving through space. This picture is useful and mostly correct for everyday purposes. At a deeper level, it is misleading. The deeper picture is this: particles are not fundamental, fields are. A field is a mathematical object that assigns a value to every point in space. A temperature field in your kitchen assigns a number, the local temperature, to every location. The field is the pattern, not the thermometer that measures it. Quantum field theory says the universe is made of fields like this, but at a much more fundamental level. There is an electron field, there is a photon field, there is a quark field for each type of quark, there is a Higgs field. Each field stretches across all of space, filling it, humming with quantum fluctuations. Every point in the universe, including the air in front of your face, is a location where all these fields have values. When a field has a localized excitation, a concentrated ripple of energy in a small region, that ripple is what we call a particle. An electron is a ripple in the electron field. A photon is a ripple in the electromagnetic field. A quark is a ripple in a quark field. This changes everything about how we picture matter. You're not a collection of tiny balls bouncing around. You're an intricate pattern of excitations in a set of universal fields. Those same fields extend out, beyond your body, beyond the Earth, beyond the solar system, beyond the galaxy. They are everywhere. They do not stop at the edge of you. Here is the important part for our story. The electron field that is vibrating inside your body, creating the electrons that hold your atoms together, is the same electron field that extends to the farthest galaxies in the observable universe. Not a similar one, the same one. There is one electron field and it fills everything. The same is true for every other field. One photon field, one Higgs field, one quark field of each type. Each stretches across the entire cosmos. This means the distinction between you and distant matter is not a distinction between separate stuff. It is a distinction between localized patterns in the same underlying medium. You're a dense, organized cluster of ripples in a universal fabric. A galaxy 10 billion light-years away is another such cluster. Between you and the galaxy, the fields continue without interruption. Think of a pond. You and the galaxy are two ripples on the surface. There is one pond. Its water is connected. The ripples are patterns in the water, and the water joins them, even as they remain locally distinct. From this perspective, calling yourself a separate being is like calling one ripple on a pond a separate thing from the rest of the pond. The ripple has its own shape and motion, yes, but it is not separate from the water. It is made of the water. It cannot exist without the water, and the water extends beyond it to every other ripple. This is how modern physics understands matter and space and the connections between distant things. Fields first. Particles as ripples. A universe that is, at root, a single continuous structure with patterns embedded in it. And once you see yourself this way, a question becomes almost unavoidable. If there is one electron field, and every electron is a ripple in it, are the electrons really separate things at all? Let us sit with this idea a little longer, because it deserves careful attention. Somewhere inside your body, there is an electron bound to an oxygen atom in a water molecule. Call it electron A. Somewhere in a quasar 13 billion light-years away, there is an electron bound to a hydrogen atom in a hot cloud of gas. Call it electron B. You might say that electron A and electron B are two different particles, living in two different places, never to meet. In the classical, particle-based picture, that is exactly what they are. But in quantum field theory, the picture is different. There is one electron field. It extends continuously from here to there. Electron A is a localized excitation of that field in your body. Electron B is a localized excitation of the same field in the quasar. They are not two different things. They are two ripples in one continuous medium. When you put it this way, something important follows. You cannot really have a private electron. You cannot own one. An electron is a feature of the universal electron field, temporarily localized in your vicinity. It is yours for a moment, and then, when atoms rearrange or chemistry happens, that same field excitation moves on, or disperses, or recombines. The field itself is impersonal, universal, shared. This explains why all electrons are identical, not similar, identical. The same mass, the same charge, the same spin. If they were independent objects, this would be a bizarre coincidence. Billions of trillions of separate electrons, all with exactly matching properties, to precision levels that no manufacturing process could ever achieve. That is not how the universe works anywhere else. They are identical because they are all the same kind of ripple in the same field. The field has a specific rule for how its excitations look. Every excitation, everywhere, follows that rule. So every electron has the same properties, not because of a conspiracy, because there is only one pattern, and every instance is an expression of it. This is a deep physical reality. You can locally detect, count, and experiment with electrons, but you cannot separate any one of them from the universal field that gave rise to it. The electron in your eyelash and the electron in Andromeda are not two isolated things. They are two places where the same cosmic field has taken on a localized particle-like appearance. The same logic applies to every particle species. Every photon you see, every quark in every proton in every atom everywhere, every neutrino passing through the universe right now, is a ripple in a field that fills the cosmos. The universe is not a collection of things. It is a set of fields with patterns in them, and what we call things are those patterns. In this view, the word connection almost loses its edge. You cannot be connected to something you are never separate from. You and the distant quasar are not two objects with a bridge between them. You are two features of one continuous mathematical object that spans the observable universe. This is not mysticism. It is the standard model of particle physics, the most precisely tested theory in human history. Every experiment ever done on particle behavior is consistent with this field-based picture. Every collider, every precision measurement, every discovery of the past several decades has deepened the case. And it leads to an intriguing possibility, one that a famous physicist entertained as a thought experiment. If all electrons are ripples in one field, might they in some sense be one electron, wandering through space-time in many guises? In 1940, a young physicist named Richard Feynman got a phone call. On the other end of the line was his thesis advisor, John Archibald Wheeler. Wheeler was one of the most inventive thinkers of 20th century physics. He had a habit of calling his students with wild ideas. Wheeler said, "Feynman, I know why all electrons have the same mass and the same charge. They are all the same electron." He explained the idea. An electron moving forward in time, when it encounters a positron, which is an electron's antiparticle, could be described equivalently as an electron zigzagging back in time, then forward again. If you imagine the whole universe laid out with time as a dimension, a single electron's path could bend, fold, reverse, and loop through space and time so elaborately that it would appear, at any given moment in ordinary time, as many separate electrons. If you sliced the universe at a particular instant, you would see the path crossing your slice many places, once for each electron in existence. In Wheeler's picture, there is only one electron. It weaves through all of space and time, forward and backward, and the thousands of trillions of electrons we see are really just one enormous world line sampled at many places. Feynman liked the idea. He even used part of it in his work on quantum electrodynamics, where positrons are treated mathematically as electrons moving backward in time. The full version of Wheeler's proposal, though, ran into problems. It would require the universe to have exactly the same number of electrons and positrons, since every time the single particle turned around in time, it would contribute one of each. Our universe has far more electrons than positrons, so the strict one-electron theory cannot be right. But the underlying intuition was onto something. It captured in vivid form a real truth about modern physics. All electrons are identical because they are all expressions of the same underlying field. In a deep mathematical sense, they are the same pattern, repeated wherever the field is excited. The reason this idea matters for our journey is not that it is literally true, but that it forces the right frame of mind. When you ask how you are connected to the rest of the universe, one honest answer is that every electron in your body shares its most fundamental nature with every other electron everywhere. They are indistinguishable instances of one universal possibility. They are, in the language of physics, identical particles, and the quantum mechanics of identical particles is different from the mechanics of distinguishable things. When identical particles interact, they must be treated as participants in a shared quantum state. They cannot be labelled as this one or that one. Their wave functions overlap in ways that no classical intuition captures. This has consequences that extend beyond labs. It means that in the quantum description of a large system, electrons cannot be treated as owned property. They are expressions of a field that knows nothing about territory. The field runs through your body, through the air around you, through the vacuum beyond Earth, through the sun, through the galaxy, through the distant quasar, without pause or change of character. Its excitations, wherever they appear, are identical. This is a picture where the ordinary distinction between inside and outside, between you and everything else, becomes much softer than our everyday language suggests. The inside is made of the same field as the outside. The field does not notice the boundary. Our skin is a boundary of chemistry, of biology, of organization, but not of the underlying substance. You are a pattern in a cosmic medium. You are local. You are real. And the medium continues, identical in character, all the way to the edge of what can be seen. The fields we have talked about so far are the fields of particle physics, electron fields, photon fields, quark fields. But there is one more field, and it deserves its own chapter, because it is the one that connects massive objects at cosmic scales. It is the gravitational field. Isaac Newton, 3.5 centuries ago, described gravity as a force. Every mass pulls on every other mass with a strength that depends on the masses and the distance between them. In Newton's picture, gravity acts instantaneously. The sun tugs on the Earth with no delay. If you moved the sun, the Earth would feel the change at the same instant. Albert Einstein, early in the 20th century, changed this picture entirely. In his theory of general relativity, gravity is not a force transmitted through space. It is a curvature of space-time itself. A massive object bends the geometry around it, and other objects move along the curves that result. What we feel as gravity is really the shape of the cosmic fabric, and that shape, Einstein realized, cannot change everywhere at once. If you shake a mass, you create a ripple in space-time. That ripple, a gravitational wave, travels outward at exactly the speed of light. Not faster, exactly the speed of light. The gravitational field obeys the same universal speed limit as electromagnetic signals. For a long time, this was a prediction without experimental confirmation. Gravitational waves are incredibly weak. Detecting them requires measuring changes in length smaller than a fraction of the diameter of a proton across instruments miles long. Unthinkably precise. In 2015, an observatory called LIGO detected its first gravitational wave. 2 black holes, each about 30 times the mass of the Sun, had spiraled together and merged more than 1 billion years earlier. The final collision sent a ripple through space-time that travelled outward at the speed of light for over 1 billion years. On a September morning in 2015, that ripple passed through the Earth. LIGO caught it. The waveform matched Einstein's prediction almost exactly. Since then, dozens more gravitational wave events have been detected. Merging black holes, colliding neutron stars, each one a faint tremor in the geometry of space-time, reaching us across vast distances after journeys of millions or billions of years. Here is what this means for our story. Gravity is a long-range field. Every massive object in the universe exerts a gravitational influence on every other. The Sun pulls on a distant quasar, if only by an imperceptibly tiny amount. The quasar pulls on the Sun. These pulls travel at the speed of light, so they are delayed by the distance, but they are real. The gravitational field links every mass in the universe to every other mass that lies within each other's light cones. You're in the gravitational field of every galaxy you can see. Their mass pulls on you faintly, Through the curvature they introduce to space-time, your mass in turn pulls on them, or will, once enough time has passed for the gravitational signal to reach. Every object in your past light cone has had time to reach you gravitationally. Its tug is part of the geometry you inhabit. This is not a poetic statement. If you calculated the total gravitational pull on your body from every piece of mass in the observable universe, you would find contributions from the Moon, the Sun, the Milky Way, nearby galaxies, distant galaxy clusters, and the most remote observable structures. Each contribution is minuscule. The sum is real. You are right now being shaped, in the most literal geometric sense, by the distribution of mass across the entire observable cosmos. That web of gravitational pulls leaves traces we can see directly in the structure of the universe. The detection of gravitational waves was not the end of the story. It was the beginning. Since LIGO caught its first signal in 2015, observatories around the world have detected many more. What they are finding is that the universe is not quiet. Far from it. The cosmos is, in gravitational terms, noisy. Black holes merge, neutron stars collide, massive stars collapse. Each of these events sends out a gravitational wave that propagates outward at the speed of light, passing through everything in its path. Those waves do not stop at the surface of planets or the edges of galaxies. They pass straight through stars, through planets, through your body. Gravity interacts so weakly with ordinary matter that detecting it requires extraordinary effort. But that same weakness means gravitational waves travel through matter almost unaffected. A gravitational wave can pass through the entire Earth without losing any significant energy. Physicists estimate that gravitational waves from various cosmic sources pass through the Earth roughly once a day, and many more events produce waves too faint for our current detectors to register. Every second, your body is being gently stretched and squeezed by incredibly small amounts as the fabric of space-time around you vibrates with signals from distant cataclysms. How small are these amounts? When a gravitational wave from a merging pair of black holes passes through a region of space, it typically stretches and compresses that region by a factor of about 1 part in 10 to the 21st. That means if you had a ruler the length of a meter, the wave would stretch it by 1/1,000,000,000 of 1/1000,000,000 of a meter. Far below anything you could ever feel. But the wave is real. It is there. It passes through your body carrying information about an event that may have happened 1 billion years ago in a galaxy you will never see. For a brief instant, the atoms of your body wobble in unison with the aftermath of an ancient collision. You're in constant, if extraordinarily faint, contact with the violent dynamics of the universe. Consider this as a kind of cosmic awareness. The universe is not silent, it is not still. It is alive with events that send gravitational messages outward. Some of those messages reach you in delicate pulsations of the space-time you inhabit. Your detectors, even if those detectors are only your own atoms responding imperceptibly, are receiving signals from the deep cosmos continuously. And here is a thought to hold on to. The gravitational waves of today are not the first that Earth has received. The planet has been bathed in gravitational signals since it formed, and so has every atom now in your body. The protons and neutrons that make up your blood have been gently wobbling to the rhythm of distant black hole collisions for billions of years. Every star that has ever died, every binary pulsar that has ever spun down, every neutron star merger has contributed to the gravitational background that your body inherits. You are a record in a very faint sense of all the gravitational history that has reached this region of space. And the gravitational field carries not only waves, it carries the slow, steady pull of distant matter. That pull has sculpted the large-scale structure of the universe itself. When astronomers first carefully measured how galaxies rotate, in the 1970s, they ran into a puzzle. The outer edges of spiral galaxies were rotating too fast, by a lot. If only the visible matter, the stars and gas we can see, were pulling on the outer stars, those outer stars should have been flung away long ago. Instead, they were orbiting stably, at speeds that implied far more gravity than the visible matter could provide. The conclusion was strange but unavoidable. There had to be more mass than we could see, a lot more, surrounding each galaxy in a huge invisible cloud. This invisible mass is called dark matter. After decades of observation, it has been confirmed many times over. Galaxies are embedded in vast halos of matter that do not emit light and do not interact electromagnetically. We detect it only through its gravity. Dark matter outweighs ordinary matter by roughly 5 to 1. For every pound of stuff you can see in the universe, there are about 5 pounds you cannot. The stars, planets, gas clouds, and living beings we know about are the visible froth on a much larger ocean of something else. And here is where our story resumes. Dark matter is not confined to individual galaxies. It forms halos, yes, but those halos connect. Between galaxies, there are filaments of dark matter linking them together. These filaments are the scaffolding on which visible matter has assembled over billions of years. Computer simulations based on the observed dark matter distribution show a striking pattern. The dark matter of the universe is arranged in a vast web with threads and sheets and knots. Galaxies sit at the densest points where filaments cross. Galaxy clusters form at especially dense intersections. Between these structures, the dark matter thins out but never disappears entirely. When you look up at the night sky, the galaxies you see are not scattered randomly. They trace this invisible scaffolding. Their positions mark the skeleton of something you cannot see directly. You are, right now, embedded in this scaffolding. The Milky Way sits inside a dark matter halo. That halo extends out to perhaps several 100,000 light-years in every direction. Beyond it, the halo thins, merging into the broader web that connects us to our neighbours, including the Andromeda Galaxy, the smaller galaxies of the local group, and eventually, through thinner filaments, to more distant clusters. The gravitational pull you feel from this unseen web shapes how our galaxy moves through the universe. The Milky Way and Andromeda are drifting toward each other at about 250,000 miles per hour, pulled by mutual gravity and by the dark matter that links them. In several billion years they will collide, but the connection is not only to our immediate neighbours. Our local group is itself part of a larger structure called the Virgo supercluster. That is part of an even larger structure called the Laniakea supercluster, a vast collection of hundreds of thousands of galaxies tied together by common gravitational flow. The Laniakea supercluster is itself a small feature in the even larger cosmic web. You, sitting in a chair, are being gently pulled by the gravity of this entire web. The pull is small, but the structure is enormous. You are one point on a net that spans the observable universe. Ordinary matter traces the same pattern. We will see that next. Dark matter provides the scaffolding. Visible matter fills it in. Together they form what astronomers call the cosmic web, and it is the largest coherent structure in the universe. Let me paint the picture. Zoom out from Earth, past the Moon, past the Sun, past the outer planets, past the Oort cloud, past the nearest stars, past the edge of the Milky Way. Keep zooming out, past Andromeda, past the local group, past the Virgo cluster. At some point you start to see a pattern. Galaxies are not evenly distributed. They're clustered along thin, bright threads, like beads on a string. Between the threads are vast empty regions called voids, where very few galaxies exist. The threads intersect at nodes where galaxies pile up by the thousands. These nodes are the galaxy clusters, the great metropolises of the cosmos. If you kept zooming out, you would see that the pattern repeats on larger and larger scales up to a limit. The universe becomes statistically uniform at very large scales, but before it does, it shows this filamentary structure. Threads, nodes, voids, a web. How big is this web? Its largest filaments are hundreds of millions of light years long. Some stretch close to 1 billion light years. The voids between them are often hundreds of millions of light years across, and a few are even larger. The nodes, the galaxy clusters, can contain thousands of galaxies, each with hundreds of billions of stars, all bound together by gravity. The cosmic web formed over billions of years from tiny density fluctuations in the early universe. Recall those quantum fluctuations that inflation stretched to cosmic scales. Those fluctuations became slight overdensities and underdensities in the primordial matter. Overdensities attracted more matter through gravity. Underdensities lost matter to their denser neighbours. Over time, the overdensities grew into threads and nodes. The underdensities became voids. You live inside this web. Specifically, you live in a part of the web called the local sheet, which sits on the edge of a huge void called the local void. The Milky Way is moving within this structure, pushed out of the void by the relative lack of matter in that direction, and pulled toward the denser regions of the Virgo cluster and beyond. The web is not only a map, it is an active structure. Matter flows along its filaments. Gas, ionized and hot, is channeled through the threads, fueling star formation in the galaxies at the nodes. Galaxies migrate along filaments toward denser regions, eventually falling into clusters. The web is a circulatory system, moving material from the voids into the population centers of the cosmos, and its threads link us to distant places. Through a chain of filaments, our galaxy is connected gravitationally, and through slow gas flow, physically, to galaxies hundreds of millions of light years away. Not directly, not quickly. But through the web, material and influence can travel over cosmic time. When you think of yourself as part of the universe, do not think only of the Earth under your feet. Do not think only of the Milky Way. Think of yourself as a node on a node on a node, embedded in a structure that fills the observable cosmos. The web is the real body of the universe, and you are one of its tiny living features. Even the particles drifting through this web, the ones that pass through your body, tell a story of the beginning. There is a particle you should know about. It is called the neutrino. It has almost no mass. It carries no electric charge. It interacts with ordinary matter so weakly that trillions of neutrinos pass through your body every second, and you never feel a thing. Neutrinos are produced in many places, in nuclear reactions in the Sun, where fusion in the core churns out enormous numbers of them, in supernovae, where a dying star can release more neutrinos in a few seconds than most of the rest of the universe combined during that time, in the atmosphere of Earth, when cosmic rays strike air molecules, in the natural radioactivity of the ground beneath you. But the neutrinos that matter most for our story come from the Big Bang itself. Just as the universe produced the cosmic microwave background of photons, it also produced a cosmic background of neutrinos. This neutrino background is older than the photon background. It was created in the first few seconds of cosmic history, when the universe was still a superheated plasma. The neutrinos decoupled, meaning they stopped interacting meaningfully with other matter, when the universe was only about a second old. A tiny moment. Before atoms, before protons finishing their condensation, before stars, before galaxies. From that moment onward, those neutrinos have been flying freely through space for nearly 14 billion years, stretching in wavelength as the universe expands, cooling down, thinning out, but never disappearing. Right now, at any given moment, there are about 300 cosmic background neutrinos in every cubic inch of space. That number includes the space inside your body. You have trillions of them within you at any instant. They are passing through, mostly without interacting at all, ghosting through your atoms like they are not even there. Over the course of your lifetime, trillions upon trillions of these primordial neutrinos will pass through you. Nearly all will continue their journey unimpeded. A handful might actually interact, scattering off a nucleus, but the number is too tiny to detect without massive specialized equipment. These neutrinos are the most ancient particles you will ever touch. Older than the oldest photons of the cosmic microwave background. Older than the atoms in your body. They are essentially direct samples of the first second of the universe, still flying, still carrying the energy they had when the cosmos was unimaginably hot. Detecting them directly has been one of the great unsolved problems in physics. The interaction cross-section is just too small. A few experiments are attempting it, and they may eventually succeed, but the neutrinos are there, waiting to be caught. The theory that predicts them is firmly tied to other well-tested aspects of cosmology, and everything we know about the Big Bang implies they must exist. Think about the shower of ancient particles you're passing through right now. The photons of the cosmic microwave background, almost 14 billion years old. The primordial neutrinos, even older. The gravitational waves rippling through space-time from distant cosmic events. The cosmic rays streaming in from high-energy sources across the galaxy and beyond. Your body is in the path of all of it. You're not shielded from the universe. You're soaking in its signals continuously. The walls of your room, the atmosphere, the Earth itself do not stop most of this. You are, in a very real sense, being crossed by the cosmos at every moment. Let us talk about something strange and taken for granted. Time moves forward. You remember the past. You anticipate the future. Eggs break into pieces, but broken pieces do not reassemble into eggs. Cups of coffee cool, they do not spontaneously heat up. Every physical process has a direction. This direction is called the arrow of time. It points from past to future. It seems obvious. It seems fundamental. But at the level of basic physics, it is mysterious. The basic laws of physics, the equations that govern particles and fields, do not distinguish between forward and backward in time. Run a film of two particles colliding backward, and it still satisfies all the equations. The motion is reversible. There is no preferred direction at this microscopic level, and yet in the large-scale world there clearly is a preferred direction. Heat flows from hot to cold, not the other way. Things age and decay. Memories only of the past, never of the future. Where does this directionality come from, if not from the fundamental laws? Physicists believe the answer lies in the initial state of the universe, specifically in the fact that the universe began in a state of very low entropy. Entropy is a measure of disorder, of how many possible microscopic arrangements, correspond to the same large-scale appearance. A universe with low entropy is one that is far from equilibrium, highly structured, with lots of potential for change. The early universe, for reasons still debated, was astonishingly smooth and uniform, which, for a gravitational system, actually corresponds to low entropy. From that starting point, the universe has been evolving towards states of higher entropy. Galaxies formed, which clumped matter in some places and emptied it from others. Stars formed and burned their fuel. Heat spread. Structures grew more complex before eventually decaying. The arrow of time you feel is a local expression of this cosmic progression. The eggs break in your kitchen because the universe, as a whole, is steadily moving from low entropy beginnings to higher entropy conditions. Your local thermodynamic processes ride on a cosmic tide. Now here is the connection. Every observer in the universe, from you to an alien on a planet near a distant quasar, experiences the same direction of time. They all have memories of the same past. They all anticipate the same future. Their arrows of time all point from the early low-entropy Big Bang to whatever comes next. This is not guaranteed by anything local. It is a consequence of the fact that we all share a single cosmic beginning, and we all inhabit the long aftermath of that beginning. If the universe had multiple disconnected starting points, or if different regions had different entropy histories, different observers might experience different time directions. In our universe, they do not. Every part of the observable cosmos is sliding down the same slope of entropy growth that started at the Big Bang. The slope is steep enough and consistent enough that every observer everywhere feels time moving forward in the same sense. You and being on a planet in a distant galaxy, should such a being exist, are travelling forward in time together. You're aging together, in step. Your clocks tick at different rates due to gravity and motion, yes, but the direction of their ticking is the same. This is a shared structure, an inheritance from the first moment. Every observer in the observable universe stands in the wake of that beginning, and the wake has a direction. But the question of how time is shared across distance has its own subtleties. Here is a puzzle that Einstein solved in 1905, and it still gives people a hard time. The word now means something precise for you, here, at this moment. It is the set of events you consider to be happening at the same time as your reading of this sentence, but for a distant observer, now is not the same. In special relativity, simultaneity is relative. Two events that appear simultaneous to one observer may not be simultaneous to another observer moving at a different velocity or in a different gravitational environment. There is no universal now that everyone can agree on. This has consequences for how we think about our connection to distant galaxies. Imagine a galaxy 1 billion light-years from here. You might be tempted to ask, what is happening in that galaxy right now? But the question, in the strict sense, does not have a unique answer. Different observers, travelling at different speeds relative to you, would define now for that galaxy differently. They might place it hundreds of thousands of years in what you call the future or past. The notion of simultaneous events at cosmic distances is observer-dependent. So what can we say about connection across those distances? We can say that the galaxy existed in our past, in a specific way. Its light is arriving here now. We can say that it will exist in our future, in a sense, because our light is still travelling toward it. But the idea of a shared present moment dissolves at cosmic scales. This might sound like a weakening of connection. If we cannot even agree on what is happening right now in a distant galaxy, are we really connected to it? The answer is that we are connected. but the nature of the connection is different from what our everyday intuition suggests. We are connected through history, through light cones, through causal structure, through shared laws and shared origin. We're not connected by synchronous clocks. There is no cosmic metronome marking out universal instants. This is actually a deeper, stranger kind of connection. It says that the universe is woven together not by a uniform flow of simultaneous moments, but by a fabric of causes and effects, of pasts and futures that crisscross each other in complex ways. Every point in space-time is linked to every other point through these chains of influence. The linkage is the geometry of space-time itself. When you ask whether you're connected to a galaxy billions of light years away, the right way to picture the answer is not as a line stretching from you to the galaxy at this instant. It is as a branching tree of possible interactions, leading backward into the past and forward into the future, tied to the light cone structure that embeds both of you in the same cosmic fabric. You share a past with the galaxy. You share a future with it, in some directions. You share laws, constants, fields, and history. What you do not share and cannot share is a simultaneous now. The universe does not support that concept at its widest scales. This is a form of humility the cosmos imposes on us. The classical idea of a universal present moment is a local approximation that breaks down once distances get large. What remains is the deeper, richer notion of a connected space-time fabric, with its own internal structure of past and future, but no single slicing into before and after that everyone agrees on. And this framework suggests something even stranger about the nature of space itself. Let me bring in one of the most startling ideas to come out of modern theoretical physics. It is called the holographic principle. It says roughly that all the information contained in a region of space can be completely described by information on the boundary of that region. This came out of studies of black holes in the 1970s and 1980s. Physicists had realized that black holes have entropy, and that entropy is proportional not to the volume of the black hole, but to the area of its boundary, the event horizon. A black hole with twice the volume does not have twice the entropy. A black hole with twice the surface area does. Think about that for a moment. Entropy, the number of ways matter can be arranged inside the black hole, depends on surface area, not volume. It is as if all the information about the interior is stored on the surface, and the three-dimensional interior is, in some sense, a projection from the two-dimensional boundary. This is the holographic principle. It suggests that our everyday picture of space as a three-dimensional arena in which things happen is not the fundamental description. A deeper description might be two-dimensional, with the third dimension emerging as a kind of cosmic illusion, a shadow cast by information on a boundary. Theoretical work in the 1990s and beyond, especially by Juan Maldacena, showed that this principle can be made mathematically precise in certain kinds of spacetimes. A three-dimensional region of space with gravity, in those models, is completely equivalent to a two-dimensional theory without gravity living on its boundary. The two descriptions contain exactly the same information. They are different languages for the same underlying reality. This is speculative when applied to our actual universe, because our universe has different properties than the idealized spaces where the holographic principle has been rigorously proven. But it has reshaped how many physicists think about space. Here is why it matters for our story. If the holographic principle applies to our universe in some form, then the information about everything happening here, everything happening in your body, everything happening in a distant galaxy, might all be encoded on some boundary of space-time. The interior of the universe where you live might be a kind of holographic projection from that boundary. In that picture, the separation between you and distant galaxies is, in some sense, not fundamental. You and the galaxies share the same underlying boundary description. The distance between you in the three-dimensional picture corresponds to certain structural patterns in the two-dimensional description. Your connection to the distant universe is encoded directly into the fabric that underlies both of you. Whether this is exactly correct for our universe remains an open question. What is clear is that the direction of physics has been to move away from the picture of separate things scattered in empty space, and toward pictures in which space itself, and the objects in it, are expressions of a more unified underlying structure. You, in this framework, are a particular pattern in a global description. The distant galaxy is another pattern in the same description. Between you, the three-dimensional space stretches, but the deep layer beneath the three dimensions does not recognize that stretching. In the deep layer, you and the galaxy are both features of one mathematical object. This is as close as modern physics has come to a formal statement that the universe is a connected whole. The holographic view makes separation an emergent property, not a fundamental one. And if separation is emergent, then so is isolation. There is a concept in physics that ties together many of the threads we have been tracing. The concept is information. Not in the everyday sense of news and data, but in the precise sense used by physicists and mathematicians. Information, in this sense, is a measure of distinguishability. Two states carry information about the universe if they can be told apart. The remarkable thing about quantum mechanics is that information, in this precise sense, is conserved. The underlying equations of quantum theory are reversible. Given complete knowledge of the current state of a closed system, you could, in principle, compute its entire past and its entire future. Nothing is ever truly forgotten in the fundamental equations. Every state evolves uniquely from every previous state. In practice, of course, we cannot track this information. As quantum states interact with environments, the information spreads out. It becomes diluted across trillions of particles. It becomes, for all practical purposes, lost, but in principle every piece of information about the past is still encoded somewhere in the universe. The universe does not forget. This has an implication that feels almost mystical, though it is a direct consequence of standard physics. The state of the universe today contains, in a scrambled and distributed form, all the information about the state of the universe in the past, including the very early past, including the Big Bang. When you look around, you do not see this information as a neat record. You see tables and chairs and people. But the deep quantum state underlying all of this carries, in some distributed encoding, the entire history of the cosmos. And that means something about your connection to distant galaxies. If every interaction leaves a trace, and if those traces spread out over time through further interactions, then the particles in your body carry subtle imprints of events that happened far from Earth, long before Earth existed. Supernovae that exploded in other galaxies, quasars that flared billions of years ago, collisions of black holes whose gravitational waves passed through the material that would eventually become you. Each of these events left traces, faint and nearly untraceable, but real, in the quantum state of the matter that eventually composed you. Similarly, the matter in distant galaxies carries traces of events here. If a photon left your body 1 billion years from now, and was absorbed by an atom in a faraway galaxy, that absorption would leave a subtle change, a tiny correlation, a wisp of information about you, embedded in that distant atom's quantum state. The universe in this picture is a vast record of all interactions, spreading and mixing and conserving every trace. This is related to the concept of decoherence and to the ongoing puzzle of what happens to information when it falls into a black hole. Physicists have argued for decades about whether black holes truly destroy information or merely scramble it beyond recovery. The current best guess is that information is preserved, even through a black hole's evaporation, by means we do not yet fully understand. The deep point is that the universe appears to be a system in which every event leaves a trace, every interaction creates a correlation, and every correlation persists in some form. You are, at this instant, a knot of correlations stretching back to the Big Bang and outward to every part of the observable cosmos that has had time to influence you. Your existence is a record, however garbled, of almost 14 billion years of cosmic history, and the universe is still writing, still creating new correlations, still expanding. Which brings us to the edge. The universe is not just expanding, it is expanding faster. In the late 1990s, 2 independent teams of astronomers measured the brightness of distant supernovae and made a shocking discovery. The expansion of the universe is accelerating. Distant galaxies are not just moving away. They're moving away faster today than they were billions of years ago. The cause of this acceleration is still mysterious. Physicists call the unknown cause dark energy. Its effect, though, is clear. Over long time scales, galaxies that are currently visible will recede faster and faster until they are receding from us at a speed that exceeds the speed of light. At that point, no light they emit will ever reach Earth again. They will cross our cosmic event horizon and disappear from our observable universe forever. This is already happening. Right now, as you read this, galaxies at the edge of our observable universe are slipping away, beyond the point where we can ever affect them or be affected by them. The boundary of what is causally connected to us is shrinking, in terms of which specific galaxies remain inside it, even as the universe itself grows larger. The far future of our cosmos, if dark energy continues to dominate, is a lonely one. In roughly 100 billion years, almost every galaxy currently visible will have crossed our horizon. Observers living then will see only the galaxies in our local group, the galaxies close enough to have remained gravitationally bound. The rest of the universe will have faded from view. This is a melancholy thought. Our cosmic connection is, in some sense, being severed over time. Galaxies we share a past with will slowly become invisible. The handshakes of the early universe will echo more quietly as the partners drift out of reach. But here is a subtle and important point. The connection is not truly broken. It just becomes one-directional and historical. Even after a galaxy passes beyond our horizon, we still carry its imprint. The light we have already received from it is still on its way, still reshaping our current moment. The correlations established in the early universe are still encoded in the quantum states of our matter. The shared history does not disappear because the future is lost. In other words, the past is permanent, the future is uncertain, and the present is a moment of transition, as more and more of the cosmos slips into the category of was rather than is. For those alive right now, this is actually a remarkable privilege. We live at an era when the vast cosmic history is still visible. We can still see galaxies 13 billion light-years away. We can still detect the cosmic microwave background, the neutrinos from the first second, the gravitational waves from distant collisions. Future civilizations, billions or trillions of years from now, will not have this view. Their skies will be darker, their universe will appear smaller. They will have to infer the vast cosmos we see directly. In a sense, we are witnesses to a great unveiling and, soon after, a great concealing. The universe made itself visible for a while, and it is slowly closing the curtains. This realization gives the current moment a particular weight. You are here now, at a time when the cosmos is still broadcasting its story. Every photon, every neutrino, every gravitational tremor that reaches you is a message that will, in cosmic terms, not always be available. You are part of a generation, on a planet, in a moment of history when the universe is still largely open to inspection. One final thought remains. We have travelled a long way. We started with a hand held up, and with the claim that every atom in it once touched every other atom in the universe. We traced light cones, causal structure, and the subtle meanings of simultaneity. We walk through the shared chemistry of stars, the universality of physical laws, the unity of quantum fields, the strangeness of entanglement, the geometry of space itself, and the quiet rain of ancient photons and neutrinos falling through your body. Now we can ask a quiet, honest question. What does it mean? It means first that you're not an object isolated in space. You are a process, unfolding within a larger process, made of the same substance as everything else you can see, bound to the rest of the cosmos by every physical thread we have discovered. You're a knot in a field, a node in a network, a ripple in a fabric that stretches out past any boundary you could cross. It means, second, that the connection between you and the distant universe is not a metaphor. It is an accumulation of very specific physical links, shared origin, shared chemistry, shared laws, shared fields, correlated quantum states, gravitational influence, exchange of light, exchange of neutrinos. Each of these links is measurable. Each has been verified in laboratories or through telescopes. They are the sturdy, unsentimental facts of cosmology and quantum mechanics. It means, third, that our everyday feeling of being a separate self, sealed inside a skin, looking out at an external world, is a useful approximation for navigating daily life. But it is not the deepest picture. At the deepest levels physics has yet reached, the world is not made of separate things. It is made of patterns in unified fields, cross-stitched by interactions, carrying the memory of their origins wherever they go. You are not placed in the universe, you are grown from it. The same hydrogen, the same carbon, the same electromagnetism, the same gravitational fabric, the same quantum vacuum. Your existence is not an intrusion into the cosmos, it is one of the cosmos's ways of existing. And this is where the word connection earns its full weight. You're not connected to the universe the way a phone is connected to a network, through a line that could be cut. You're connected the way a wave is connected to an ocean. You're the ocean, doing a particular thing, in a particular place, for a particular while. This is a scientific claim, not a mystical one. It is built from measurement, from equation, from theory tested in laboratory and observatory. Every piece of this picture has been independently verified. Put together, they tell a story that the scientific tradition took centuries to assemble and is still refining. For those of us alive in this moment, the story offers something unusual. It offers an understanding of your place that is both extraordinarily humbling and extraordinarily elevating. You're tiny in terms of size compared to the observable cosmos. The galaxy you live in is a rounding error compared to the full web, and yet every particle in you is bound, by the deepest laws of physics to every other particle in that web. Your atoms are cosmic. Your presence is cosmic. Your awareness, at this moment of the universe you belong to, is the cosmos pausing to know itself for a brief time from one of its many vantage points. The distant galaxy, 13 billion light-years away, is sending its light through the fabric we share. You are receiving it. This is what connection means when we take the physics seriously. This is where our journey ends.